Nobody's here. All right, so welcome to Math 140 Business. This is lecture number 21, November 18th, 2021. We are now going to do chapter 22. And chapter 22 is essentially the last chapter that's going to be on test number 2. According to my little syllabus here, 23 is also on the test, but 23 is a review chapter. It's a summary. This book likes to throw in these summary chapters every now and again. So there's no new information in it. So this is the last chapter that will actually be on the test. I'm going to start sharing my iPad. And let's see, I got marked absent and Mr. Roll Call. My audio is having issues. I'm here. Okay, I will update you. One more person is here. Okay, so where is my, okay, there we go. Okay, so chapter 22 is inference in practice. Inference in practice. So, remember that when you do confidence intervals, when you do hypothesis testing, basically the one major flaw in the structure of a low-level stat class is that you can't justify and prove why things are true and why the conditions are necessary to be able to use given formulas, because the mathematics of the justifications is just too advanced. And I'll be honest, a lot of what we do, I have learned because I've taken a lot of advanced classes, but some of the things, some of the statements, some of the conditions, it's just like, even I haven't learned them. They're just more advanced than what I've done. And again, for me, just like you, it's like, okay, I don't know why this is necessary. Why do I need a sample of this size, but anything smaller does not work? Why do I need them to be independent? Why does it have to be an SRS? Why this, why that? I don't always know the deep answers for things, but I do know and have a list or a flashcard or some kind of note structure where it says for every situation, to be able to use this formula, make sure you have this satisfied, make sure you have that satisfied, make sure this isn't the case, make sure this is the case, and etc. So every formula that we've done, confidence intervals, hypothesis testing, etc., know when we're allowed to use it. And because there could be conceptual questions, like on homework, like on tests, like the final, where it gives you some information and says, am I allowed to do it in this case? And if not, what am I lacking? Oh, well, it doesn't have an SRS. Oh, well, your sample size is not large enough. Oh, well, they're not independent, whatever the case may be. So make sure those are all down. That's like the first portion of the chapter. It's just be aware that in practice, you need certain conditions to be satisfied. And as the semester has progressed, I have given you those conditions as we've come across them. The part about the chapter that I really do want to focus on, the part that's a little more mathematical, is twofold. And we're going to start with the difference between type 1 versus type 2 errors. There are two ways of making a mistake when dealing with hypothesis tests. So I'm going to make a table here. It's a 2x2 table. So there's going to be 2 rows and 2 columns. And the columns will be, the columns will be categorized by whether or not the null hypothesis is inherently true or false. Now, it's got to be one or the other. Either it's true or false. Now, I will never know whether it's true or false. I can only reject something or not reject something based upon what my evidence says. But I will never know for certain whether it's true or false. So this is more of a conceptual thing. Conceptually, the null hypothesis is either true or false. But in terms of what I do, I can do two things. At the end of my work, I could reject the null hypothesis. And at the end of the work, I might fail to reject the null hypothesis. Those are the two conclusions that I can make. And these are the four possible scenarios. In two of these four scenarios, I have made a good call. I have done the right thing. I have done what I was supposed to do. Which two of these four boxes, upper left, upper right, lower left, lower right, which of these four boxes, which two of them did I do the right thing?
The top right and then the bottom left.
Yes, the top right and the bottom left. If the top right, if the null hypothesis is false, I would like to reject it. So if I do reject it, I have made a good decision. For the bottom left, if the null hypothesis is true, I don't want to reject it. So if I fail to reject the null hypothesis, I have made a good decision. Does that make sense so far?
Yes.
Yes.
Yeah.
Okay, now, the other two boxes, on the other hand, if the null upper left, if the null hypothesis is true and I reject it, I made a mistake. I made an error. I don't know that I made an error because I don't know if the null hypothesis is true. But, you know, the man upstairs, if you believe in that, if not the great turtle in the sky, whatever it is that you believe, something out there knows that an error was made. And if the null hypothesis is false, then I would like to reject it. So if I don't reject it, I've again made an error. Again, it's not an error that I'll know that I made, but it is an error. So these two types of errors, the one on the top left, if the null hypothesis is true and I reject it, I call this making a type 1 error. And the probability of making a type 1 error is nothing more than the significance level of the test, which we have a symbol for. We've been using the symbol alpha. Every hypothesis test has a significance. Usually, what is the significance if they don't tell me otherwise? What have we been using as a significance for this whole course if they don't tell me otherwise?
The standard deviation.
And that will be a no, but thanks for playing. Try again tomorrow.
90%.
No.
Oh, 0.05.
Yes. I was so upset for a second that you actually were on the right track and then you stopped yourself. So I'm glad that you.
Yeah, and then I recuperated my skills, and that was.
Yeah, I'm very glad to see that. So yes, we've been using 5% as my significance level. The probability of making a type 1 error. Because let's think about it. Let's assume, for example, that I have a null hypothesis that says, you know, mu is equal to some value, mu naught, with an alternative that mu is greater than mu naught. So what do? I take a sample and I will reject the null hypothesis if I land in this region over here, correct? This is my rejection region. Or my critical region, correct?
Yeah.
Now, if the null hypothesis is true, and remember, we are assuming it's true if we're going to be making a type 1 error. If the null hypothesis is true, then what is the value at the center of this distribution?
Zero?
Not 0. Well, it is 0 if I switch to a standard normal distribution.
It'd be mu.
It'll be mu naught. Remember, mu is just what I think the parameter is. Mu naught is a specific value. So if the null hypothesis is true, the center of my distribution is mu naught. And what is the probability of being rejected? The probability of being rejected means that I land in this region over here. Because that's the rejection region, right? If I'm going to reject, it means I land in that region over there, correct? Well, what is the area of this? Normally it's 5% or alpha. So the likelihood of being rejected, of making a type 1 error, the likelihood of landing in the rejection region, the likelihood of landing past my cutoff point is just by definition what I've been calling the significance level of the test, alpha. So alpha is the probability of making a type 1 error. The other situation is not rejecting the null hypothesis when it's false. And what type of error do you think we call that? Now, this is a tough one, but I think you can do it. What
Type
type of,
2.
hey, you got it. So this is called a type 2 error. Unfortunately, type 2 errors are a little more challenging than type 1 errors. Why should that be the case? Well, let's think about it. For a type 2 error to occur, the null hypothesis has to be false. So let's look at the example that I have there. I have the example that the null hypothesis, the mean is some value, and the alternative is the mean is greater than that value. Well, if the null hypothesis is false, what is mu equal to?
Something greater than M naught?
Something greater than mu naught. Do I know what it is?
No.
No, it could be anything bigger than mu naught. Which means, while I know it's bigger than mu naught because the null hypothesis is false, I don't know what it is. So the power of a test against a specific alternative, the power of the test against a specific alternative is 1 minus the probability of a type 2 error for that specific alternative. Every possible alternative has a power associated with it. The power of the test against a specific alternative is 1 minus the probability of making a type 2 error for that specific alternative. So let's do an example of this. So here we have an example.
I'm sorry.
Yeah, question?
Yeah. Can you go over the part after probability of making a type? Like just this part, the
Well,
part, the loop,
on the top or the bottom?
the after the graph. So where the smile after the smiley faces.
So, oh, wait, up here?
Yeah, that like this whole until where you stopped. Can you explain it one more time?
Hey, you want me to go over all of this?
Yes, please.
Okay. So the probability of making a type 1 error is also called the significance level of the test. And it is denoted by alpha.
Okay.
Why is it equal to the significance level of the test? Well, if the null hypothesis is true, then my curve has mu naught at its center. The rejection region in this example is the far right. And I know that the likelihood of landing in that rejection region is just 5% usually. It's just my alpha. That's how I pick my alpha. I need a result that has less than a 5% chance of occurring. I'll then reject the null hypothesis. So any result past that point has less than a 5% chance of occurring. So anything in that last 5% would be my rejection region. So alpha is the area of that rejection region. That is the probability of making a type 1 error. On the other hand, if the null hypothesis is false, that means mu is equal to something else. Now, there's lots of possibilities. Every single one of them, I can compute what's called the power of the test for that specific one. And it's going to be 1 minus the probability of making a type 2 error for that specific alternative. That's a definition, the power of a test. So all you need to do is evaluate it for a specific example. And I'm going to do a specific example right now.
Thank you.
With me so far?
Yes, thank you.
Okay, so there's an example here. So example 22.4. Okay, so it says the following. It says finding the power of the test for a population mean for a normal population with known standard deviation is less challenging than most other power calculations, which is why we're going to use it here. Okay, so we have the following. Here's the example. We have alpha, my significance level is 0.05. We have a situation where the null hypothesis is mu is equal to 0 against the alternative where mu is strictly greater than 0. We have a known sigma equal to 1 for this example. And we have a sample size that's equal to 10 for this example. Okay.
Nice.
So even before we worry about power and any of this kind of stuff, let's draw the situation here. Okay. What's this? If the null hypothesis is true, and remember, we always draw our curves assuming the null hypothesis is true. What's the center going to be?
0.
The center is going to be 0. If the null hypothesis is true, the center is going to be 0, correct? And we have a sample of size 10. So what is the standard deviation of this particular sample distribution?
One.
Well, 1 is the standard deviation of the underlying population distribution. But here we have a sample of size 10.
Maybe the standard deviation divided by the square root of n or
Right. So in this case, it's 1 over the square root of 10. Do we agree with that, Anahit?
Yes.
Maybe the difference, yeah, remember the difference between the population deviation, the population standard deviation, and the sample standard deviation is that for the sample, it shrinks by a factor of 1 over the square root of 10. Okay. This is what we have so far. So if I want to have an alpha of 0.05, what value corresponds to an alpha of 0.05? Well, I could certainly calculate the z value from my calculator, although we should already know how to do this. What is the z value for 0.5% to the right? What's my z score going to be? Or my z star?
90?
Not 90. I mean, it's z is you know, when you switch it from a regular distribution to a Z distribution,
If it's
Yep.
90%, it should be 1.645. Probably.
it is 1.645.
I still remember.
Yeah, because remember, if you have 5% on the right, that means the center is 90%. And a center, okay, hold on, this mosquito, I'm gonna slam it. All right, so that gives me a Z of 1.645, and we know that Z is equal to my sample value. Yeah. Minus the assumed mean if the null hypothesis is true, divided by 1 over the square root of 10. Ha! Die. Oh, that's just disgusting. Okay, so what do I get? What is my X bar equal to? What is my sample cutoff? Solve that for X bar. What sample size will make me reject my null hypothesis? Anyone? 1.645 equals X bar divided by the square root of 1 over the square root of 10.
Would X bar be equal to 0.52?
X bar is 0.520. So in other words, any sample value past 0.520 for a sample of size 10 would make me reject the null hypothesis. With me so far?
Yes. I'm just confused as how do you got that equation? Like the Z-score equals X bar minus 0, 1 square root of.
Well, remember your formula for Z, it's data minus mean divided by the standard deviation, correct?
Okay.
So that's my Z, that's my data, that's my mean if the null hypothesis is true, and that's my standard deviation. So it's just a Z, it's a Z-score formula from like chapter 3 or something like that,
Okay.
right?
Yeah, I was just I didn't remember it to be
And it
honest.
is interesting on the heat. It is interesting. It's very interesting. Because at the end of the day, your cutoff value, if you decide to do a hypothesis test, then you want to know precisely what results are going to make me reject the null hypothesis and what results are going to make me not reject the null hypothesis. Sure, calculating p-values is great, but I can only do that once I have my answer. Here's my sample, so here's my p-value. Oh, okay, that p-value is small, so here's what we're going to do. Or that p-value is large, so here's what we're going to do. But sometimes even before you take the sample, you want to sit down and say, okay, what's my cutoff point? What are the values of which I'm going to reject and not reject? In this case, because it's alpha equals 5%, the probability of making a type 1 error is 5%. My cutoff is right there where Z is equal to 1.645. So I can use that formula to calculate that my X bar is 0.520. Any average past 0.52, I'm going to reject. Now, if I do reject the null hypothesis, it's because I think the mean is greater than 0. So for this particular example, suppose mu is actually equal to 0.8. Suppose mu is actually equal to 0.8. If mu is actually equal to 0.8, if that's the actual average, where will the peak of my normal distribution actually be located?
What did you ask? My bad.
If mu is actually equal to 0.8 instead of 0, like I've been assuming until now, where is the peak of my normal curve going to be located?
Is it still in the middle?
Well, it's only in the middle because that's where 0 is located. Because my null hypothesis said, hey, mu is 0. Okay, mu is 0. Let's make my curve centered at 0. But now we're saying, no, it's 0.8, huh?
Slightly to the right.
How much is slightly? Where's 0.8 located?
Oh, it depends on where one is.
Well, 0.52 is right here.
Yeah, it'd be located to the right of where the point 0.05.
Yeah, that's 0.5. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. So the actual curve would look something like this. If mu is really 0.8, then we'd be over there. The center should be over there, correct?
Yes.
Okay, so what's the probability of making a type 2 error if mu is actually 0.8? Well, let's think about it. What is a type 2 error again? What does it mean to make a type 2 error?
When the null hypothesis is false, but you don't reject it.
Well, here it's false because it's 0.8 and I'm not going to reject it. Where exactly underneath this purple curve would I not reject it?
It's to the left of 0.52.
Exactly. This is my non-rejection region. Because remember, 0.2 is the cutoff point. Any results to the right of 0.2, I reject the null hypothesis. Any results to the less than 0.2, I don't reject the null hypothesis. Whether it's equal to 0 or not doesn't matter. It's still 0.52 is going to be the cutoff point. So this is the probability that X bar, my average, is less than 0.520. If mu is really 0.8, given that mu is really equal to 0.8. So let's compute this. What's the probability that X bar is less than 0.52 given that mu is equal to 0.8? Well, I can convert X bar by subtracting the mean and dividing by the standard deviation. What do I get when I subtract the mean and divide by the standard deviation? I turn X or X bar into what? When you subtract the mean and divide by the standard, when you take your data and you subtract the mean and divide by the standard deviation, what do you get?
Z-score?
You get your Z-score. So we just want the probability that Z is less than negative 0.885. How do I calculate the probability that X is less than, Z is less than negative 0.885?
Inverse norm?
Inverse, not inverse norm,
Uh,
regular norm.
oh, yeah, regular norms.
So what do I get? I never want you know how to do this. We've been doing this all year. The probability that Z is less than negative 0.885, even if you're not following anything else. This is something from chapter 3, or maybe 4. I don't even remember. And you what? Can you explain the last part about the type 2 error? Which part? Can you be more specific?
Like where you started with the mean equals 0.8. You kind of like lost me there.
All right. So the red curve is your original curve if the null hypothesis is true.
Mhm.
It's centered at 0. The deviation, 1 over the square root of n, sigma over the square root of n.
Yeah.
Right now, alpha is 0.05, which means I can compute the cutoff point. I can compute the z value of the cutoff point is 1.645. Anything to the right of 1.645, and I am going to reject the null hypothesis. That's the 5% cutoff point, 5% on the right side of the graph. With me so far?
Yeah.
Okay, so now somebody comes along and says, you know what? I just talked to God. God knows the truth. And he told me, or she, or it, or they, I don't know, but whatever, that mu is not 0 like you assumed. Mu is really 0.8. And you're like, oh shit, mu is 0.8? Man, my curve's in the wrong place. Because the curve has to be centered at mu. So because it came from God, I chose purple because purple is royalty. I moved and I make my curve to the right and see how it's centered at 0.8 now?
Yeah.
Okay. But the cutoff region hasn't changed. 0.520 is still the cutoff point. Anything to the right of 0.520, I reject the null hypothesis. Anything to the left of 0.520, I don't reject the null hypothesis. So if I want to compute the probability of making a type 2 error when mu is 0.8, what does it mean to make a type 2 error? That means I don't reject the null hypothesis. So I want to the left of 0.52, that purpley shaded region. I want to be less than 0.520 if mu is really equal to 0.8. Well, how do I calculate that? Isn't X bar dependent on the M? What the hell's the M? Or is that like the, you were eating something and it tasted good, so you kind of went off on a tangent. So what do you mean X bar dependent on the M?
Mu.
No, X bar does not depend on you. X bar is your sample average.
Thanks.
So X bar is, we're looking for the likelihood that X bar ends up to the left of 0.520 when mu is really 0.8. Well, if mu is really 0.8, then all I'm going to do is convert this to a z-score, which is what I do in the second line and the third line. And then I go to my calculator. I subtract the mean, which by the way is 0.8, God told me. And then I divide by 1 over the square root of 10. And when I do that, I get z less than negative 0.885, which my calculator tells me is what?
Is it 0.188?
0.188. The probability of making a type 2 error if mu is really 0.8 is about 19%. And therefore, the power of the test for mu equal to 0.8 is how much? What is the power of the test for mu equal to 0.8?
1 minus 0.19 or
Yeah, which is how much?
.81 or
0.812. That is the power of the test. So for this particular example, the probability of making a type 1 error is 5%. the probability of making a type 2 error for mu equal to 0.8 is 0.188. Are these acceptable? So at the end of the day, you don't want to make an error at all, right? At the end of the day, you'd like to make no error. So you'd like to make your probability of making a type 1 error smaller, and you'd also like to make the probability of making a type 2 error smaller, correct?
Yes.
But let's see what happens if you do that. And this is very conceptual, so you got to follow this. If you want to make the probability of making a type 1 error smaller, you're going to make your alpha smaller, which means that red area in the graph is going to be moved and it's going to be smaller to the right. Do you agree? My cutoff point is going to move to the right. Do you agree with that?
Yes.
But that means if I move it to the right, then the likelihood of making a type 2 error, which is being to the left of it, goes up because that's more shading. If I move the cutoff to the right, the purplely shaded area gets bigger. So by making a type 1 error probability smaller, I will automatically be making the probability of a type 2 error bigger. And vice versa.
So it's give and take.
Well, there's only one way to make both of them smaller. And that is to do what?
Bigger, is it a bigger significance thing?
Well, significance is your alpha, right? We just said if you change alpha one way, the other one will go the other way. So
Widen the interval?
I'll say again?
Widen the interval?
One more time?
Would you like widen the numbers you can take, like confidence?
This is a hypothesis test. There's no confidence interval here,
Oh, okay then.
right? A hypothesis test. If I make my probability of a type 1 error smaller, I make the probability of a type 2 error bigger. If I make the probability of a type 1 error bigger, sorry, if I make the probability of a type 2 error smaller, I make the probability of a type 1 error bigger. In other words, you make one smaller, other one gets bigger. It seems like you can't handle both at the same time. But there is one way to make them both smaller. And that is to do what?
Do you have a larger sample?
Yes. Yes. The only way to make both smaller simultaneously is to make a larger sample, which makes all error probabilities smaller. Because the bigger the sample, the more accurate your results or how close they are to the true value. So if I want to make both smaller, I need a larger sample. Now, when I teach Math 3, I haven't taught it in years, but when I used to teach Math 341, I vividly recall going through the mathematics of determining the sample size necessary in order to ensure that both your type 1 error probability and your type 2 error probability are sufficiently small. It's kind of like the formulas that we had earlier in the book for computing the sample size for a given margin of error. Right? I actually was working with someone during the break on this. If you have a given margin of error and you want to compute the sample size, we did that earlier in the course. So it's very similar, but the math is a little more complicated because you're doing with two things at the same time, trying to make sure both probabilities are small enough and figuring out what sample size is necessary to ensure that happens. It's not hard. You can do it with algebra. You don't need anything more advanced than that. But nevertheless, it's on the upper end of algebraic sophistication versus your standard, basic algebra. So it's usually not done. But nevertheless, I can ask if there are any questions. I get the impression that not everyone's understanding this, but does anyone have any specific questions on it?
No.
Well, let's do another example anyway. In fact, you know what? Rather than taking one from the book, I have an idea. Let's do the same problem, but this time have a sample of size 20. Let's see what having a sample of size 20 does to everything. So we have another example. Alpha is still 0.05. The null hypothesis is mu equals 0 versus the alternative where mu is greater than 0. Sigma is still 1, but this time n is equal to 20. So let's start like we did last time with drawing our normal curve. Oh, that was a pretty good. Wasn't okay. I always the end is always. Hey there, what do you think about that one? Yeah. Woo, that's what I'm talking about. Okay, so what is the number in the center?
0.
0. And what is the 5% cutoff mark going to be? I'll give you my answer. It hasn't changed.
It's
1.645.
1.645. That hasn't changed. However, if I use my z-score formula, what will my formula be in this case?
It'll be,
divided by square root of 20 instead of.
Yeah.
X bar minus 0 over 1 over root 20, which gives me an X bar value of
0.368.
okay. I get an X bar value of 0.368, which means in order to reject the null hypothesis now, any result past 0.368 is enough. Now, first of all, does that make sense, by the way, that the X bar should be smaller now than it was for the last example? That my rejection points, the point at which I'm going to reject anything further, the critical point, is actually closer to 0 as opposed to further away?
yes.
It better make sense because that's what the math gave us. But can you explain why it makes sense?
Because since you have a larger sample size now, your error should be smaller. I know.
Touchdown, exactly. Since you have a larger sample size, the expectations are that you're going to be closer to the true value, which means you don't have to go as far away before you have an irregular or unlikely result. Fantastic. Love it. Okay, now suppose let's go to purple, or let's go to what color should I use for this one? I don't think I've really had your input throughout the year for color, so I'll do it right now. What color should I use for the second one? How did I find X bar? I just solved the math right there in the corner. 1.645 equals X bar minus 0 over 1 over the root 20. Cross multiplied, bam, X bar equals 0.368.
Bright pink.
Right, bright pink. Is that the one at the top right?
Yes. No. Yeah.
Okay, because I also have those colors.
Oh, there's more.
Yeah, I have
But
more.
I want the cool green one.
Is that the second row, third one, or second row, fourth one?
Second or third one.
You got it. Okay, so now suppose that mu is actually equal to 0.8. So where should my normal curve be centered if mu is really equal to 0.8?
To the right of the z-score.
Well, yeah, this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. It should be there, far enough off to the side. I'm going to make it a little more exaggerated. Something like that. Oh, okay, like that. Okay. If it's really 0.8, it should be centered over there. So now what's the probability of a type 2 error for, is that the word I used? If mu is equal to 0.8? Well, what exactly is a type 2 error? Remember, a type 2 error means not rejecting the null hypothesis. Not rejecting the null hypothesis means that I end up over there to the left of 0.368, right? It's the probability that my sample average is less than 0.368, assuming, of course, that mu is equal to 0.8. So how do I compute this? Well, I can subtract the mean, which is 0.8, and divide by the standard deviation, standard error. And I get less than 0.368 minus 0.8 divided by 1 over root 20. Of course, this is still assuming that mu is equal to 0.8, which gives me the probability that z is less than negative 1.933. And I then go to my calculator and I compute it, and it gives me about 0.0266. So what do you notice about the probability of a type 2 error when the sample size went up compared to the last one?
It got smaller.
It got smaller. It got smaller. The alpha stayed the same because I chose alpha to stay the same. And the probability of a type 2 error drops. If the sample size goes up, then they drop, or if I keep one the same, the other one drops. But I have the choice of making both of them smaller had I wanted to. Does that make sense?
Yes.
And you can compute the power or the probability of a type 2 error for every different mu value. Okay, you can do it for mu 0.7. You can do it for mu 0.6, for 0.5, anything bigger than 0, you can do it for. And you could actually graph what's called a power curve. And then you can use the power curve to help, like everything else we do in statistics, to help analyze the situation and help, picking a sample size to do what you want and everything you need. I mean, it's just, the more you have at your disposal, the more you can use.
So can you give us like
Professor,
an example?
Oh, whoa there, buddy, 2 at once, that's crazy. Someone take a number. So who's going first?
You can go.
Go
first.
ahead, brother.
Wow, your guys are both so sweet. You go, no, you go, no, you go. Michael, go ahead. I think one of you was Michael. Fine. Alberto, go ahead.
I was just gonna ask if you could give us an example we can like work on our own and then see if we got it right.
You want to do one yourself without my input? I love it. Let's take a look at the workbook. Let's see what we got in here.
I was gonna ask, where did we get the negative 1.933 from?
0.368 minus 0.8 divided by 1 over root 20.
Oh, never mind.
Well, you can't never mind after I answer the question.
Thank you.
You're welcome. So let's take a look. Chapter 22. Okay, chapter 22. They have nothing in the workbook. Wow, sucks to be them. All right, let's get one from the book then. Oh, actually, you know what? What the hell? I have an idea. Ready for this one? First, new color, please. Anahit, what color?
Let's do the cyan looking one.
Like a car? What the hell's a scion?
You know what? Just the
Blue.
one the diagonal from it.
That one right there?
Yeah.
Okay, we'll do a car. Okay, so here's what we're gonna do. Example, alpha equals 0.05, H naught, mu equals 0, HA, mu equals 1, sigma equals 1, n equals 10. But this time, do mu is equal to 0.7. And you wanna try it yourself. I'll give you a couple seconds. I gotta check Facebook anyways.
Dave, with wrong questions, please.
Okay, is that enough of a time or you guys want a little more time?
No. Like one, 2 more minutes. 1 or 2.
All right. Geez, all right, fine.
I'm just in the zone.
I love it. Love it. Must be the car.
What should we round it to?
A few decimals. I don't care. 3 decimals is fine. Okay, ready?
30 seconds.
30 seconds. Okay, I gotta go. So you guys, if you're still working, still work, but I'm going to go ahead and do it. The first thing I'm gonna do is I'm gonna draw the original curve with its center at 0 and its cutoff point over here at 1.645 with its X bar minus the assumed null hypothesis of 0 over 1 over root 10. In fact, we already have that for the first one, which was 0.520. So Z is equal, sorry, X bar is equal to 0.520. That's my cutoff point. And then suppose, in this case, that mu is equal to 0.7. If mu is equal to 0.7, I don't think I've ever used that color. So 0.1, 2, 3, 4, 5, 6, 7. If mu is equal to 0.7, then I have a curve that looks like this. So the probability of making a type 2 error is the probability of being to the left of 0.520. So the probability of making a type 2 error, if mu is really equal to 0.7, is a probability that X bar is less than 0.520 if mu is really equal to 0.7, which is equal to the probability that X bar minus 0 over 1 over root 10 is less than 0.520 minus 0 over 1 over root 10 if mu is really equal to 0.7. Oh, whoops, not 0, 0.7. That's the mean. Probability that Z is less than 0.520 minus 0.7 divided by 1 over the square root of 10, negative 0.569. And then this gives me equal to, so what did everyone get? Is your final answer?
I got 0.215.
I got 0.285.
Oh,
I got 0.285.
where on the calculator did you go for that? I can double check.
For which part? Do you have me up to here?
Like, yeah, up to there, like calculating it.
I went to normal CDF, 0.5, negative 0.569. Normal CDF, negative 0.569, boom, 0.285. On the heat, did you get it?
No.
So
Oh,
for the lower part, you put 0.5.
for which part?
So you're doing normal CDF on the calculator. So I just want to know the parts like lower, upper, mean, and then the sigma.
The lower would be negative 99999.
Yeah, I mean, Z is less than this number. Lower is negative 99999 and negative 0.569 and Z, so 0 and 1. Z is always 0 and 1. Yes, no, maybe so? Anyone? Hello?
I'm still not getting it. I don't know why.
Which part?
Like I'm like putting the stuff in the calculator. So like lower, or you know what? No, I'm actually doing it. Give me 1 second.
Okay, I'll wait.
Okay, I got it.
So what you notice, hopefully you notice, is that for n equals 10, we got 0.188 when mu was 0.8. And we got 0.285 when mu was 0.7, which makes a lot of sense because the lower the mu, the more my new curve shifts to the left, the more my shaded region grows, which is why it's a higher probability. Also, the closer mu is to 0, the more likely it is that I'm going to have a result in the vicinity of 0, which is what the null hypothesis is claiming. So again, there's a higher likelihood of making a mistake because if you say, no, mu is not 0, mu is really 0.01, then it's so close that it's hard to predict what the data is going to suggest. The further away you go from 0, the more clear of a distinction it's going to be because my curves really separate. Hopefully you got that. If not, it's all recorded. So you're more than welcome to watch my videos. Please like and subscribe and up my views so that my what's it called? That analysis? I don't know.
What's your YouTube channel again?
What's my YouTube channel?
The name.
MCPC Learning. MCPC Learning. So maybe I'll give extra credit to everyone who subscribes. You don't even gotta like listen to them, but like if I can get to like a gazillion people, I can make tons of money. And make sure your videos make the YouTube algorithm. What does that mean? Is there a YouTube algorithm?
Yeah.
Yes.
So can I do something different on my end to ensure that? How does that work?
I think one way to get more interactions is you make shorter videos.
Oh, well, I mean, these videos are the length they are. What can I do about that?
Yeah, there's like different stuff.
Okay, so we should like every video and then we should make like a bot army to like them. So I have like gazillion likes.
That's literally against YouTube's terms of service.
Now, who the hell asked you? All right, say who. Okay. So does MCPC stand for Moorpark? No, it stands for math, chemistry, physics, and chess. The only 4 things in life I'm good at. Those are the 4 things that I tutor and teach. Math, chemistry, physics, and where's my A? Oh, on a heap. So talk to me after class, after everyone else leaves, and we'll see about that A. All right. I can't, of course, do it. Oh, crap. I'm being recorded. Oh, no. I can't do anything now. Oh, well, on the wink, wink, maybe, talk later. We'll see. But yeah, no, seriously, guys, if you want to sub and just, you don't even gotta like ever listen or watch them. But if I can get like every semester, everyone to subscribe, I'll eventually hit like, I don't know, 1,000. When do I get money? 1,000?
You get money if your video just gets a lot of, well, you have to put an ad in your videos and you make money from the ads.
I put the ads in or YouTube automatically puts the ads in?
Well, you have to enable ads.
I have to. Is it not automatically enabled?
No, I think you have to get to a certain point and then they allow you to roll ads on your video.
I
Gotcha.
think
So you
you
get
can have-
1,000 subscribers first, and then you get like the ability to put ads.
Thousands?
Something like that. I think. I don't know.
All right. Let's see. How many subscribers do I have?
71. I just subbed.
71. 71. Guys, I have so much longer to go. All
Yeah,
right.
I just subbed right now, so 73. I think it's out.
All right. So yeah, okay. We'll have to get extra credit to everyone who subscribes. Not a lot. Don't think I'm gonna like raise your grade a ton, but like from like a D to an A or something like that. Okay.
Percentage though.
That sounds perfect.
Yeah.
Yeah.
All right. If there's any other questions before we stop for today. Oh, I only have 2 more hours of tutoring tonight, so it's gonna be a short night for me. Okay, so could you post this lecture tonight? I always post a lecture right when class, well, it takes me like a half an hour to get it up there, but yeah. As soon as I close it, I download it. And today I had to go home right away, because I got a tutor later, but then when I get home, I upload it. So it'll be like an hour.
How long does it take for you to upload since it's an hour?
It usually takes about 15 minutes.
Oh.
For the entire process. For like these videos are like an hour, 15 minutes. It usually takes about 15 minutes to go through the process. It does something. It's like I don't know. It just takes that long. All right. Anywho, so we'll stop